On pattern avoidance and alternating sign matrices.
Thank you. Thank you for inviting me. I'll be talking about something that many people in the audience are experts on. So hopefully I have something new to say. Before I say that, I would like to say how I got into this, and it was almost entirely because of Professor Ayyer. So I was a student in the physics department here and doing some field theory, which is some part of physics. I found some combinatorial identities and which I could not prove, and I tried very hard. And then I just said, okay, let me just see if there's someone in the mathematics department who would know something. And the most interesting web page by far was So I sent him an email one Monday morning explaining in detail who I was and blah, 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 and whether you would be kind enough to have some time to help me. And within 5 minutes I got a reply saying, come now. So I came and I met Teddy there the first time also, and that's how that's how I've become interested in combinatorics. And recently I've gotten very interested in alternating sign matrices. And of course this is an ideal birthday present for Professor Ayyer because of course he was the first one to prove it. So here is what I wanted to say. So Professor Ayyer has the distinction of being well known among two sets of species. Among humans he is fairly famous, not because of the community here, but because not all humans are mathematicians. But among computers, he is legendary. And in fact, as Lara remarked, Shalosh Biekad is the Paul Erdős of computers. So, unfortunately, we have not been able to program computers to celebrate Beethoven's birthday. So that is an assignment for us. Their 80th birthday conference. So that I wish you many happy returns. And so here's what I'll be talking about. Monotone triangles. I'm sorry I'm using monotone instead of dog because I want to define something else using dog. So I'll talk about monotone triangles and I'll show you how 3-1-2 avoiding permutations have some natural structure in their monotone triangles. And then I want to generalize the story for alternating sign matrices. So that's what I'll do. And in the process, I'll show you that there is a natural sub-bijection, meaning between Gogs and Magogs, in the sense that there's a subset of Gog triangles and a subset of Magog triangles which are in very natural bijection. And those are related to the avoidance of this 3-1-2. So just to remind you, a monotone triangle, and I'm using notation which is different from yours, but which was there in the Mills-Robbins-Ramsey paper. So a monotone triangle is a set of integers arranged in triangular form as shown, where each entry is strictly less than the entry to the right of it. Each entry is weakly less than the entry above it, and weakly less than the entry along the diagonal to the right of it. And the second condition says that the bottom row is just 1 through n. Okay. So here is an example. So I have 4, 3, 4, 1, 3, 4, 1, 2, 3, 4, and this is this corresponds naturally to the permutation 4, 3, 1, 2. Basically, what I do is I just look at the new entry in each row, and that is the next element of the permutation. Clear? So permutations, of course, are only a subset of, correspond to only a subset of monotone triangles. So right now I'm just talking about them. So there's a natural bijection between monotone triangles and alternating sign matrices, which, okay, I don't really want to go into. But the number of alternating sign matrices is given by this beautiful formula, which was first proven by Professor Ayyer. So now I want to define another structure on monotone triangles. And I say that there is a gap at row I if there is a j such that aij minus ai plus 1j, aij minus ai plus 1j is greater than 1. So in this example, there is a gap at row 2 because 3 minus 1 is the lemma. Okay. Okay, so now I directly go to 312 pattern. 312, the notion of 312 avoidance. So I consider a permutation of the letters 1 through n. I say that it contains a pattern 312 if there are positive integers I, j, k, such that, when ordered in that way, such that pi I is greater than pi k is greater than pi j. So this is the 3 greater than 2 greater than 1 condition. So the number of such permutations is counted by the Catalan numbers. I think the first result in this direction is due to mathematics, but I'm not sure that 1, 3, 2 avoiding permutations, 1, 2, 3 avoiding permutations are also counted by the Catalan numbers. Okay, so here's a remark on the structure of this pattern avoidance. That is that if there is any ijk in a permutation that contains the 312 pattern, then there exists another integer L such that there's another 312 pattern at L plus 1k. So the 3 and the 1, I mean, you will find a 3 and a 1 which are adjacent. And the proof just comes by looking at, I mean, if I already have ijk, I just look at the entry pi I plus 1. If it's less than pi k, then I plus 1k is the thing, and I'm done. If not, then I plus 1 jk is the new 312 pattern, and I just write it until I plus 1 gets k. Okay, so it's always the case that you will find two consecutive fellows. I mean, 3 and 1 will be consecutive. So in this example, 5, 4, 2, 1, 6, 3, which is a permutation of order 6, it has a 312 pattern as I showed here, 5, 1, and 3. But I look at I plus 1, which is 4 here, but 4 is greater than 3, so 4, 1, 3 is the new permutation, is the new pattern. And then I look at 2, but 2 is now less than 3, so 4, 2, 3 is that pattern. Okay, so this is just a remark. And the result is that, this is the mini result of our big result. Oh, by the way, I should say that this is joint work with Robert Cori, who is at Bordeaux. So, okay. Permutation contains a 312 pattern if and only if there is a gap in the corresponding monotone triangle. And in particular, if the 312 pattern occurs at I plus 1j, the gap has to be at row I in my conventions. Okay, so there's a natural structure on monotone triangles which corresponds to 312 avoidance for permutations. And I don't have time to go through the proof, although it's not too hard. The main idea is that I look at the prefix up to let's say L, and there cannot be a 312 pattern at LL plus 1k if there is no 312 pattern at LL plus 1k if the set of entries in the permutation before j such that they are larger than pi of j is no, it's correct. Okay, sorry. Let me go through. So I look at the lth entry. I look at all the entries in the permutation before the lth entry, such that they are larger than pi l. If this is a consecutive, if this is a set of consecutive integers, then there cannot be a pattern at l plus 1k. So this is a tiny lemma that we need to show the lemma that I tell you here. And this is what you would like to generalize for alternating sign matrices. So if I have, I need some notion of 312 avoidance for alternating sign matrices to be able to generalize this. And for that, I need to have, I need to be able to write it in word form. So I need a generalization of, I need some set of words which are counted by alternating sign matrices and which are in natural bijection with ASMs. So I define a GOG alphabet, which is given by tuple